In this presentation, we study one of the most common bottlenecks in logistics facilities, the truck gate. A gate is not just a checkpoint. It is the first queue in the system, and it can amplify downstream congestion when trucks arrive in waves. Our goal is to analyze a single truck gate entry process end to end and show how you can improve throughput, reduce waiting, and keep security and compliance intact. The goal is to analyze and optimize a single truck gate entry process. The main performance indicators are waiting time, throughput in trucks per hour, make span as the time to complete the work in the planning window, and how balanced gate utilization is across available booths. If you optimize only one metric, you can break the system in another way. For example, maximizing throughput without controlling queuing can create long waits and unpredictable service, while balancing utilization without respecting peaks can cause hidden delays. We focus on a realistic operating context. Pacific Coast Distribution Center serves the Los Angeles metropolitan area and processes over 2,000 truck movements per day through a constrained gate infrastructure. During peak hours, truck waiting times can exceed 45 minutes. During off-peak periods, gate utilization can drop below 60%. Management wants to reduce average processing time by about 30%, increase daily throughput by about 400 additional trucks, and still maintain security and compliance requirements. Gate entry becomes a bottleneck because arrivals are time varying. Even if the average arrival rate is manageable, peaks create bursts that exceed service capacity and build queues. The system is also heterogeneous. Different truck types and different documentation requirements create variable service times, and limited booth capacity means small inefficiencies compound. Finally, congestion feedback from the yard can slow gate processing when downstream space or equipment is constrained. Tier 1 builds a complete baseline model. We represent gate operations as a network flow with capacity constraints and queue dynamics, so we can reason about arrivals, service limits, and waiting systematically. The purpose of this tier is clarity and accountability. A full model forces you to name the sets, parameters, decision variables, objective, and constraints, and it helps you identify which limits are structural and which are operational choices. We define a set of nodes that represent the processing stages, such as the arrival point, the gate booths, intermediate processing stations, and the departure point. We also define a set of directed connections that represent allowed movement from one stage to another. We index time in discrete periods, so we can express time-varying arrival rates and evolving queues rather than assuming a static average. Key parameters include the arrival rate in each time period, service rates for each processing connection, and capacity limits that represent how many trucks can be processed simultaneously. We also include average service times and waiting cost weights, because we want the model to capture both operational delay and the cost impact of time spent in queue. The decision variables represent how many trucks are flowing through each connection in each time period, how much waiting accumulates on each connection, and how long the queues are at each processing node over time. In plain terms, these variables let you track three things at once: how much work you push through, how long trucks are stuck waiting, and where the queues are building. The objective minimizes total system cost, combining waiting time cost and processing delay cost across all time periods and all processing connections. Operationally, this objective prevents a common failure mode, pushing trucks through one stage aggressively while creating an unbounded queue at another stage that appears later in the process. Flow conservation enforces that what enters a node must either leave that node or remain as a queue. We represent arrivals at the start of the network and departures at the end of the network. To keep narration unambiguous, think of this as a start node where arrivals are injected into the system, and an end node where completed trucks exit the system. Capacity constraints enforce that the number of trucks processed on any connection in a time period cannot exceed the capacity limit for that connection. This is how the model respects the physical bottleneck. Each gate booth and each downstream station can only process so many trucks per unit time. Queue dynamics describe how queues evolve over time. The next period's queue equals the previous queue plus new inflow minus the service that can be completed, limited by the service rate. This matters because waiting is not a static penalty. Waiting is an accumulated state that grows when inflow exceeds service and shrinks only when service catches up. The model includes a lower bound linking queue length to waiting time. If a queue exists at a node and service is limited, then waiting time must be at least proportional to the queue divided by the service rate. This prevents a modeling loophole where the flow variables imply congestion, but waiting variables stay artificially low. Non-negativity constraints ensure that flows, waiting times, and queues cannot be negative. This is basic but important because it keeps the model physically meaningful and prevents the solver from using negative values to cancel costs. This visualization shows the system as a network. Trucks arrive, pass through gate booths and checks, and then depart into the yard or the next stage. Use this picture to map each mathematical element to a real operation. Every arc is a processing step, and every node is a place where queues can form. Consider a simplified example during peak time. The arrival rate is 20 trucks per hour, and there are 2 gate booths with service rates of 12 trucks per hour and 15 trucks per hour. An illustrative outcome is system utilization of 73.3% and an average waiting time of 2.1 minutes per truck. The key lesson is that even with 2 booths, imbalance and variability can create queuing if capacity is not allocated well. Tier 2 introduces a deployable heuristic, list scheduling using a priority queue. As each truck arrives, you assign it to the gate that minimizes expected completion time based on the gate's current workload. This approach is fast enough for real-time decisions. In words, its running time grows roughly with the number of trucks times the logarithm of the number of gates, which keeps it practical even at high daily volumes. The visualization shows the priority-based list scheduling idea. You maintain a queue of arriving trucks, estimate processing times, and dispatch each truck to the best gate choice given the current state. The model is simple, but it captures a powerful idea. Dispatching decisions should depend on current gate load, not just arrival order. In the example results, makespan is 23.33 minutes. Average waiting time is 1.94 minutes, and average utilization is 78.5%. Interpretation matters. The heuristic balances work across gates and keeps waiting low without requiring heavy optimization tooling. This code section defines the truck data structure and the gate state representation. The state typically includes each gate's next available time and current assigned workload. Correct state tracking is essential. If a gate's availability is miscomputed, the heuristic will send trucks to the wrong place and create avoidable queues. This part defines the priority rule for choosing which truck to schedule next, such as urgency, service time estimate, or compliance flags. The priority rule is the policy lever. Tight compliance scenarios may prioritize documentation complex trucks earlier to avoid downstream delays. This section computes the estimated completion time for each gate if it were assigned the current truck, then chooses the gate that yields the smallest completion time. This is the core dispatch rule. Minimize the completion time increase while still respecting constraints and service characteristics. This part updates gate availability and records the schedule: arrival time, start time, waiting time, and completion time. These outputs are not just for reporting. They are the metrics you need to audit whether the gate is behaving as intended in real operations. The final part summarizes results such as makespan, average waiting, and utilization per gate. Per gate metrics are important because average utilization can hide imbalance. A single overloaded gate can create a long queue even when system-wide utilization looks acceptable. Tier 3 upgrades the search with particle swarm optimization. Instead of making one dispatch choice at a time, PSO searches over a policy space, such as gate weights and dynamic priority factors. The objective combines waiting time, makespan, and utilization balance. This tier is useful when simple dispatch rules plateau and you need a better global trade-off. The update step describes how particles change their candidate solutions over iterations, guided by each particle's best-known solution and the swarm's best-known solution. In plain terms, the swarm explores multiple policy settings at once, and it gradually shifts towards settings that consistently reduce waiting and improve balance. The fitness function is the scoreboard for a candidate policy. It should reward low average waiting time, low makespan, and balanced utilization, while penalizing unstable or infeasible behavior. Fitness design matters. If utilization balance is ignored, the algorithm may over-optimize one gate and recreate the same bottleneck under a different policy. The framework is initialize particles, simulate or evaluate each candidate gate policy, compute fitness, update particle positions, and iterate. Even when PSO is used, you still need operational interpretability. You should be able to explain what the learned gate weights and priority factors mean in terms of real dispatch decisions. In the example improvement, average waiting time decreases from 1.94 minutes to 1.23 minutes, representing about a 23% performance gain over the heuristic baseline. The improvement also includes better utilization balance, meaning fewer situations where one gate is overloaded while others sit underused. This code part defines how a particle encodes a gate policy, such as numeric weights per gate and factors that adjust truck priority dynamically. Encoding is critical. If the encoding cannot represent meaningful policies, the swarm will search a space that does not contain good solutions. This section defines how to evaluate a particle by running the gate assignment logic under that candidate policy. The evaluation must compute the same key performance indicators you care about operationally: waiting time, make span, and utilization balance. This part computes the particle's fitness from the simulated results and records the particle's personal best if it improves. It also updates the global best across the swarm, which drives convergence toward the best performing policies. This section implements the update step that changes particle positions. It is how the swarm mixes exploration and exploitation. Practically, you can think of this as testing many dispatch knob settings and learning which settings work best under the observed arrival patterns. This part often includes convergence tracking, such as the best fitness per iteration and the stability of the policy parameters. Convergence matters operationally because you want a policy that is robust across days, not one that performs well only on one simulated dataset. The final part outputs the best policy discovered, along with the schedule metrics and per-gate utilization. This output is what you would hand to operations leadership. Not just that the method is better, but exactly how much better it is and why. Tier 5 steps beyond local gate optimization and models the terminal as a system of systems. A digital twin simulates the gate, the yard, equipment availability, and even traffic-aware departure timing as a connected whole. This matters because the gate is not independent. Yard congestion and equipment constraints can slow the gate, and gate surges can overload the yard. The digital twin lets you test interventions without disrupting live operations. The architecture integrates modules for gate processing, yard congestion and allocation, equipment availability, and predictive analytics for bottleneck detection. The key idea is closed-loop coordination. Data updates the simulation identifies risks, and optimization suggests actions such as rebalancing staffing or changing dispatch logic. In the example simulation, duration is 480 minutes, and the system processes 187 trucks. Average system time is 18.4 minutes, and throughput is 23.4 trucks per hour. The analysis breaks down gate utilization, such as about 74.2% for Gate 1, 81.7% for Gate 2, and 68.9% for Gate 3. This helps you see where capacity is stressed. This code part defines the simulation environment and event logic for arrivals, service start, and service completion. Good event logic is crucial. If events are misordered or time is updated incorrectly, the digital twin will misestimate waiting and make incorrect recommendations. This section models gate booth behavior and connects it to downstream yard state. The point is to capture feedback. When yard zones congest, trucks may take longer to clear the gate process, increasing system time. This part includes metric tracking, such as system time, throughput, queue lengths, and utilization over time. Without consistent metrics, the digital twin becomes a visualization tool instead of an optimization instrument. This section introduces bottleneck detection logic, for example, identifying the most congested gate or yard zone. In the example, bottlenecks include Gate 2 capacity severity around 73% and a yard zone congestion severity around 62%. This final section typically outputs the simulation summary and the recommended interventions. Examples include capacity expansion at Gate 2 to increase throughput by about 12%, predictive yard allocation to reduce congestion delays by about 18%, and traffic-aware departure timing, saving 8.3 minutes of average system time. The practice questions guide you through building the complete network flow and queue dynamics model, implementing list scheduling and evaluating key performance indicators, and implementing particle swarm optimization and analyzing convergence. They also ask you to extend the system with Tier 5 digital twin simulation and integrate forecasting and bottleneck prediction. Start with a complete model to understand bottlenecks and constraints. Use heuristics for real-time dispatch decisions. Use meta-heuristics when you need better global trade-offs across waiting, make span, and utilization balance. Digital twins enable predictive system-wide optimization. They help you see that the biggest improvements often come from coordinated interventions across gates, yard operations, and timing policies, not from tuning a single local rule.